Okay, hi all, welcome to the second physics symposium for this semester. We are very happy today to host Ricardo Carretero Gonzalez from San Diego State University. Let me say a few words very briefly about Ricardo's academic steps and scientific contributions. So Ricardo did his bachelor in physics at the Mexican National University. Then he moved for a PhD in applied mathematics and computation at Queen Mary and Westfield College, University of London. Then he did his first postdoctoral research position. He obtained his first postdoctoral research position at the Center for Nonlinear Dynamics at the University of College London, and then he moved to as a postdoctoral fellow again at the Department of Mathematics and Statistics at Simon Fraser University at Vancouver, Canada. Afterwards, he moved as an assistant professor at San Diego State University, where now he's a full professor in mathematics at San Diego State University. He's a co-founder and co-director of the Nonlinear Dynamical Systems at San Diego State University. He is an active advocate of dissemination of science at high schools and science festivals. And besides publishing numerous manuscripts, he has published also 3 individual books. His research interests revolve around spatiotemporal dynamical systems and chaos, nonlinear waves, including vortexes, solitrons, nonlinear breathers, nonlinear time series, and Bose-Einstein condensates. We're very happy to have him today here. She will talk about vortices and vortex rings in quantum superfluids and quasi-particle approach. We're very much looking forward to your talks. Thank you very much.
Thank you for the ominous introduction. I know Simos for a few years when we coincided in Boston, and since then we had a lot of fun doing research and also Mexicans and Greeks, some of these we get together very well. So first I want to tell you a little bit about kind of my motivation of doing these type of problems. I have a tripolar disorder, so I just have to be forthcoming with you. I do not know if I'm a physicist, an applied mathematician, or a computational scientist, right? So what I'm going to show you here is a little bit of this tripolar disorder, and I'm going to do it in a way that hopefully will be at the level that most of you or all of you are going to understand. I was told that there will be more students than faculty. So this talk is not for the faculty. Forget about the faculty. It's just the students and me that we're going to have this conversation. And if you have questions, don't hesitate to ask me. The whole point is about getting a good kind of dynamics going. I know that some of you are going to meet after the talk for 1 hour, so we can also talk there. I'll be very, very happy to talk to you. So I want to show you here. It's beautiful. Well, how can I say something about my little kid being beautiful? So this is my little kid. Every parent says my kid is beautiful, right? I see these ugly kids. Oh, you see my, yeah. For me, this is beautiful. But the reason this is beautiful is because I'm going to show you a series of steps going from the actual experiments on condensed matter physics, post-secondary real experiments, and then we're going to do some simulations that are going to be at the level of partial differential equations. We're going to do some reductions, and we're going to take that these doping beams that are in my system are going to be kind of quasi-particle-like. So these vortices, I'm going to take them as if they were kind of particles, where they have a very, very simple interactive potential between them. So I'm going to be able to reduce this spatial temporal system that is complicated to a system of ordinary differential equations, like you see with planets, that you have the kind of Newton type of flow of motions. And from there, we're going to do a little bit of math, not very complicated, all the fixed points and stability and bifurcation, to see some very, very interesting bifurcation problems and stability problems that hopefully I will be able to go all the way back, not only to the Euler model, to the PDE model, to the physical model, but actually going all the way back and say something meaningful about the actual experiments. But in these routes, I have to bring you up to speed on all these processes. So that's my point today, to try to go all the way from the physics to this bifurcation process that we can do with dynamical systems. So just a little bit about the group that I'm working with, a fun group of people there that we are all of us really applied in San Diego State. So when we say applied mathematicians, we don't do proofs. I don't give a shit about proofs because I'm a math person, but I'm really at heart I'm a physicist. So it's really about applying the math for something useful, not putting theories that on my field. It's important for theories, but that's not where I am. So we have a very nice group of people that have at least a bipolar disorder. Most of us, we have a tripolar disorder. That is the math, there is the science of application, and there's the computation. In my case, the science of application is physics because of my upbringing as a physicist. Okay? A bunch of students that are working with me on this or have worked with me on this, I would like to thank them because it's been instrumental to get the results going. This is not just to overwhelm you to say, Professor Carretero has done a lot of research. No, I want just to stress that this talk is being with other two Greek guys, not this Greek guy, other two Greek guys. For some reason, I get Greeks attacked. So I have hundreds of papers with these people, very fun people, and I would like to point out the experiments that you're going to see there are the experiments in Depot in Amherst College in Amherst in the East Coast, and he has a beautiful lab with undergrads. So he received a prize, I think 7 years ago or so from the NSF to be the best lab for undergrads. And we were doing these very beautiful experiments on condensates. So I would like to stress that the experiments that you're going to see there, they are basically these guys running this, the lab, but they're done by undergrads. So just to motivate you guys, undergrads or grad students, you can do great stuff if you get into a lab and working with the good people. And all these guys are actually experiments. I want to do math that is related to experiments. And then there is a long list of collaborators that I also would like to thank for all their work and friendship, including Simos and Leah that I have worked with them for the past 3 years or so. So a little bit of what the roadmap is going to be. I'm going to give you a very, very quick, short, bird's eye view of Bose-Einstein and condensation. What is the equation of motion that comes from looking at the mean field of these condensates? I'm going to motivate what we're going to be talking about to show you some experimental pictures where I have vortices, and I'm going to show you how these vortices are doing the dance, the volts, and moving around. Then we're going to try to study in more detail what are the dynamics of these vortices when you just take two vortices and interact with each other. And how do they move, they rotate, they run, what do they do? Okay? And connect that with the experiments. We're going to see some very nice bifurcations. And time permitting, this is really time permitting. And it depends on the interaction. And sometimes it's not even interaction. The way I feel about talking, sometimes I don't even get to the 3Ds. So we will see if we get those 3Ds. We're going to talk about, hopefully, if I have time, about vortex rings. So these are generalization of vortices in 3 dimensions. It's basically when you blow a smoke and then you do these smoke rings, something similar that in a condensate and with these microscopic vortex rings. And you can treat them also as particles, and you can do all sorts of little kind of nice tricks. And extra time, I'm for sure I'm not going to be able to talk about that. Some numerics, so forget about it. For sure I'm not going to have that. So I'm going to try to focus a little bit more on physics because all of you will do that. So this is the matter equation that comes from assuming that you have a very dilute gas of bosons. The bosons can actually overlap in the quantum state compared to fermions. So if you have a very, very cold, not cool, because cool is only good science, I mean cool in the sense of temperature, a very cold collection of these bosons, Bose and Einstein predicted that in the beginning of the 1900s, that this gas of boson should go and a phase transition in which these collections of bosons will go into a single quantum state. And the idea is it's rather simple, at least simplistically speaking. We know that particles at the quantum level have a specific wavelength. That wavelength is given by this de Broglie wavelength, right? And this de Broglie wavelength, in the denominator to P, the momentum, n times V. If you think about temperature, temperature related to velocity, vibrations of the molecule. Kinetic energy is related then to velocity. So if I reduce the temperature of my system, is that I'm reducing the velocity, the internal velocity of the beast of my system. So that velocity goes into the denominator of the De Broglie quantity. So I have 1 over 0. If the temperature goes to 0, the velocity goes to 0, so the De Broglie wavelength goes very, very large. So if we are a collection of bosons, there is an interparticle distance that is the mean interparticle distance of all of us. It will be around 2 meters or so. Okay? Don't get me that. You should actually go into international units. So don't use blood feet or whatever. I know that we're in the States, but don't do that because otherwise you have accidents like almost space telescope, but blind or bad has myopia because then you have a confusion between the units. The thing that went into Jupiter and crashed because they mixed square feet by whatever and newtons and there's just meters. So our mean intermean distance is around 2 meters. But imagine if the temperature is cool enough so that our wavelength is of the order of magnitude of our interparticle distance. Then we start to communicate. And if we start to communicate, we synchronize. So what is a Bose-Einstein condensate? A Bose-Einstein condensate is nothing but a collection of particles that they share the same quantum state. So this is just crazy because now I have a collection of whatever 10 to the 5, 10 to the 6, 10 to the 7 particles. They're all in the same quantum state. What does this mean? It means that all these particles behave like a single quantum particle, but the signal is amplified by 10 to the 7, and all of them are distinguishable of each other. So I can do quantum mechanics at the macroscopic scale. And when I say macroscopic scale, the condensates are just microns, but microns is macroscopic in the sense it's not quantum, where Planck's constant and whatever quantum mechanics start to play a role. It's actually macroscopic dynamics. Okay? So now I have these collections of bosons that all are in the same quantum state that are described by a single particle kind of scenario. Okay? I don't know. If I want this rate, the talk is going to be 2 hours. But I think this is fun. I'm going to continue a little bit this way because I get the phrase and I think you're liking this. I get to more or less whatever I want to cover. And if I don't cover, but just 10% of the talk, I don't care. If I'm just getting fun and you're actually learning some physics. Okay, so let me continue a little bit in that direction. So, what is a condensate? How can you look at a condensate? A condensate is to matter what a laser is to light. Okay, and you're a physicist, so you should be able to answer for me this question. What is the difference between a laser and the light that comes out from there? It's not a arbitrary question. This is a true question. And whoever opened their mouth right now, just shut up because you're getting the answer. Let others speak. Because you're a physicist. So I literally do this and I go 10 times and it doesn't work. So what is, let me try again. So what is the difference between this and just normal light? Go ahead. Answer, not the person answer. What is it? You don't know what is the difference of a laser? That's a laser. No, that's not a laser. This is a laser. What is the difference? You physicists. So they say coherence again. Okay. When I don't give the talk to physicists, people start saying, oh, monochromaticity. No, you can have normal light that is monochromatic. So that's not the answer. And they go, intensity. No, this does not burn. Go to the stadium and put your hand close to the floodlight. It will blow your bloody hand. Okay, so it's not intensity, it's not monochromaticity. The important thing is coherence. So matter, coherent matter is a condensate. So it's a bunch of atoms that are coherent at the level of a quantum. So it's all these atoms that are dancing the same quantum dance. So they're all coherent at the quantum level. That's a condensate. Okay. In order to model these guys, what you do is you think of, I'm not a single particle person. I'm a multiple particle person. So we're talking about 10 to the 5, 10 to the 7 particles. If you're a hardcore physicist, what you do is take the Hamiltonian of each one of them. And what is the Hamiltonian for the whole thing? It's a bloody stupid sum of all the interactions and all the terms of it's just a gigantic Hamiltonian of all these terms, right? I don't want to do that. It's almost impossible to do that multi-body Hamiltonian theory with so many atoms. What I want to do is what's called the field. So I'm going to describe the whole field, the whole set of condensate as a B field, just the density of where they are. In fact, the density doesn't tell you the whole story because in a quantum mechanical object, you have a wave function, and the wave function is not only about its mode square. The mode square of the wave function gives you density, but that's just the mode square. Don't forget that the wave function is a complex wave function. So the complex wave function has phase. So it's very important to get the phase and the density structure of this. Okay. So when you do a mean field and you do a little bit of cooking and juggling, it turns out that when you do this multi-body Hamiltonian theory and you do a mean field description, not only you get the stereotypical Schrödinger equation term, which is the kinetic term, and an external potential where you put all the atoms on the condensate, but you also get this very, very funky term. This funky term is actually a cubic term. You see that it's a square and a cubic here. So it's just absolutely crazy stuff here. Microscopically, it's nonlinear Schrödinger that's linear. All these Hamiltonians are linear. But overall, because of the way these guys are colliding, it behaves like a nonlinear system. And you might not appreciate this, but this is just crazy. Microscopically, it's linear, but macroscopically speaking, as a collection, it works nonlinear. And this nonlinear term is absolutely essential to hold in my mean field description certain entities, certain solutions that only exist because the system at the macroscopic level is a nonlinear system. Okay? So this is what is called the nonlinear Schrödinger equation. Or in the world of physics, and condensate matter physics, it's called Gross-Pythagoras equation. That one describes the wave function by condensate. And it's true and honest good description, provided the temperature is low enough so that I can describe my condensate. And phi is my wave function. You're physicists, so you are used to these wave functions. Just remind you for putting your foot on the ground that if you want to measure something in the experiment, you measure densities. So you just take the mode square, and that's what the experimentalists will see normally. There are ways to measure phases and whatnot, but usually you eyes what they will see is just intensity. Okay. So now we're going to be talking about the wave function on a condensate. The condensate has to be levitated. The reason it has to be levitated with very strong magnetic fields is that because in order to have my wavelength to be of the order of the interparticle distance, I need temperature of nanokelvin. Nanokelvin is not like a very small number. These are bloody temperatures. Nothing in the universe has that temperature. The background radiation is way, way, way hotter than nanokelvin. So the people that produce these things in experiments, that they won the Nobel Prize for these experiments that were produced in the 1900s by Bose and Einstein, they got the Nobel Prize basically because of the technological feat to finally go to low enough temperatures to create something that was predicted. Okay, nanokelvin, super, super, super cool. So if you put that into a vessel, the vessel itself will be hot enough that will evaporate the condensate. What is the only way to get the condensate going? You levitate it into a very, very strong magnetic field. And you say, how can I levitate atoms or whatever? Well, they have a very, very, very small moment of magnetic moment, so they can levitate. In fact, you can Google later, levitating traps in magnetic, levitating frogs in magnetic fields. They put these frogs in very strong magnetic, and you see the frog like this, levitating, is because the molecules of water have a very small magnetic moment. So you can actually get very strong magnet, even levitate a frog. If you can levitate a frog, you can actually also levitate a 10 to the 5 to 7 atoms micro drop of lithium or deuterium very, very easily. So now that you're levitating this trap, you have this magnetic trap that is holding the condensate, and you can play all sorts of tricks. In that magnetic trap, you can have a three-dimensional trap with the 3 magnets here, the 3 coils, are more or less of the same intensity. So you get a little ball, you get like spherical condensate. But if you make one side of the trap much, much stronger, you can create like a pancake kind of trap. So you can actually do 2-dimensional dynamics of that partial differential equation in 3D. But that Laplacian that you see here in 3D goes into 2D Laplacian. Or you can make it very strong in this direction very strong in this direction, and you can create what's called a cigar-shaped condensate. And now you can create a 1D condensate, and in the 1D condensate, you have other type of structures, okay? So in this talk, we're gonna concentrate not in one-dimensional condensates where you can have bright or dark solidus. We're gonna concentrate in a 2D condensate. We have one confining direction, two loose directions. I'm gonna get a pancake condensate. So think about my condensate to be a pancake, and the pancake is gonna have certain density. And that density is the one that I'm describing with this Gross-Pitagoric equation. Maybe I'm gonna get to vortex rings, but at the rate and point, I don't think I'm gonna be able to go through it. Okay, questions so far? As I tell my students, I talk a lot, speak a lot. If I speak a lot, I don't breathe. If I don't breathe, I die. You need to call the ambulance. Every time you speak, I get a chance to breathe. So if you like me, don't let me die. Please speak so I can breathe. Questions? Well, please. Okay, let's continue. We'll have plenty of time to talk after the talk anyway, if there are questions there. So we're going to go to two-dimensional condensate. Now let me show you a picture of a condensate typically done in the experiment of David Hall in Amherst College, where I have this condensate that is a pancake, and I'm going to photograph the, not me, they call it photographing the pancake, and it's giving you the density of this condensate. Since we are trapping the condensate in these magnetic coils, these magnetic coils at the very center, they look harmonic, quadratic. So typically speaking, I'm going to have in 3 dimensions these traps that are going to look like this in all of the dimensions. But again, it's flat, so let me look at 2 dimensions. So I'm going to have this pancake that's going to have certain density, but it's going to be in 2 dimensions. Okay, and this I'm plotting in this direction, the density here. Okay, so you're gonna see now a photograph from the top of the density of atoms that are contained in the trap. So because the trap has a minimum here, there's gonna be a maximum density here. That's what you're gonna see. All right. So this is what you see. And in the process of making this condensate, my friend here, the condensate with a little pattern. Okay, and then created some sort of tornado. That's called a vortex. And that little hole there is just the lack of atoms because of the centrifugal force pushes the atoms out. The vortices are really thin. Okay? But in order to photograph this, because it's so small, they need to remove the magnetic trap, let it go down, because there is no trap. The whole thing wants to expand. So it expands like 1 or 2 orders of magnitude, and then the holes start much more quicker because the tornadoes are so thin that there is more like centrifugal force, they expand. So you see that the vortex core looks like 1/10 of the radius of the cloud. That's just an imaging procedure after I drop, and they're really thin. Why I'm making a point about this? I want them to be quasi-particles. And the particles to be far away from each other. If you have 2 planets that overlap, the laws of Kepler do not go to hell. If I want to apply Kepler, the planets have to be separated. So I'm making a point that in the real in situ scenario, before you expand and photograph, they're very thin. They're like 1/1000th of the thickness of the condensate. So they're really thin, they are really quasi-particles. But the beauty of the expansion that you can also see them is that we're still thin, the photograph will not be able to see them. So you gain 2 things. You can photograph them and then get thicker. Okay. So let's see what happens in this scenario when I put a vortex inside a trap. Okay. So before I do that, let me just ask you what's going to happen. Okay. So let's suppose that I have a flat, infinite condensate, not in a trap, but I have an ocean of condensate, homogeneous, and I put my vortex. Okay. What's going to happen to that vortex in this infinite homogeneous condensate? What's going to happen? Nothing. Why is nothing? Why is not moving? Because it's homogeneous. That's mathematics. If you have an isotropic equation, and in that isotropic equation, you have an isotropic medium, and in that isotropic medium, you have an isotropic solution, you don't break the symmetry. You don't break the symmetry, why is one direction more preferred than the other? There are no preferred directions. If you have no preferred directions, then you don't move. So it's not gonna move. So the next question, what happens if I introduce a background density gradient? And now I have this mountain. Okay, so I'm gonna have gradients all over the place. What happens if I introduce a gradient for my vortex? What's gonna happen to the vortex? So it's gonna go. It's gonna, so what did you get? What's gonna happen to the vortex? If you put it at a background, it's gonna go where? In the direction of the gradient down, because everything falls down. Okay, you see the picture there? The vortex has the property of more mass or less mass? The mass. The bloody vortex is not a mass object, it's a massless object. So when you have a bottle of wine and then you turn it, the bubbles go down. The bubbles goes up. So I give you a second try. What happens if you put a vortex and then you apply a gradient of the potential? What's going to happen to the vortex? It's going to go up. Then wrong again. This guy has angular momentum. And because it has angular momentum, all of you have done classical mechanics. And then you have done the experiment of the wheel that you actually hold with your hands. And then you apply a force in this direction. What happens with the wheel? It's perpendicular to the force. It's called the Magnus force. So the vortex is not going to go downhill. It's not going to go uphill. It's going to go perpendicular to the gradient. Okay? So you have a mountain that is isotropic in all the directions. If you do cat 3, what is a perpendicular to the normal? It's going to be natural. Okay? That's cat 3. Therefore, a vortex has to move in a circle. Just because I know that the force is perpendicular to the gradient. Are we good? Physics, basic physics. So let's see if indeed the vortex actually does what it's supposed to do. So it does. It does kind of does. Okay. And this tells you when you do the experiment the sign of the vortex. Because if you turn the wheel in one direction, it will just go in one direction. If you turn the wheel in another, it will turn in the opposite direction. So the Magnus force is going to have opposite sign. So this guy went anti-clockwise, so this is a minus vortex instead of a plus vortex. It was rotating in one direction or the other. When you see the density, you don't know. If you have a picture of a tornado, you don't know in which direction it's turning, okay? Until you see in which direction it's spinning. Same thing. All right, so that's what happens with one vortex. Now, the question is, what happens if I have more than one vortex in my condensate? What starts happening to these little jumping beams? So I have now two vortices. I do not know if it's a plus and a minus a plus, plus, a minus a minus. So let's see what happens to this. Up to imaging or to noise, happen. So how is that possible? Nothing moves, like stationary steady state. That's wrong. Let's try to think about what's going on in here and why do we get stationary state for these two vortices. So I have my condensate. This is called the Thomas Irving radius, kind of the average size of the condensate. And I'm going to have a vortex and anti-vortex. So I'm going to put here a plus, and here I'm going to have to put a minus vortex that are at the same distance from each other. So what is the plus doing? The plus is making the fluid go in this direction. So this vortex is going to have an effect of this one, because this tornado makes this. So it's going to make a little velocity in this direction. Okay? This is a minus vortex, so it's not rotating in this direction, it's rotating in this direction. So it's going to make this vortex go like this. Yes, when you have a plus and a minus vortex, when you have one paddling in the lake, and you do this, you see the little vortex behind, you have a plus and a minus, and you see how these guys go together. The plus and a minus will go together parallel to the line of sight. But also, the plus vortex, because it fills the background of the density, is going to go in an isocontour and it's going to go in the opposite direction. And this goes in the opposite direction as this. So this is what the trap is doing, and this is what the vortex and vortex interactions are. This is the exact place where you have a balance. Because if you get them too close to each other, their interaction is going to make something really strong. And here the gradient is on the top part. The top part has very small gradient. It's very small. And if you're very close to the edge, the vortex, because they are far away from each other, is small. And here the gradient at the edge is a very large gradient. So you see that there is going to be a specific distance where these forces are going to annihilate each other, and it's going to create a steady state where nothing moves. Really interesting, eh? We're going to get some models that are going to predict what this distance is, and not only that, if you perturb that distance, what's going to happen? So, quick question for you. That's the steady state. What is the steady state? I put it there, doesn't move. That's steady state. But the steady state could be stable or could be unstable state. What is your guess for this guy being stable or unstable? So let me just ask, who votes that this guy is stable? 3.5 people. Who votes that this state is unstable? More people. And half of the people don't know shit or they don't care. They don't even raise their hands. Okay, let me tell you. Did you observe the steady state? Did you observe the steady state? Yes, therefore it's stable. How many times have you gone to the street and you have seen pencils like this, upside down? I've been 55 years in this planet and I walk all the time, every single second I'm looking for pencils upside down. Are they there? They're not there. Is it a steady state? Yes. If I align the center of mass of the pencil with the center of mass of the earth, with the point of contact, and I ask the whole universe to stay quiet, this is a steady state. Do you observe them? No, because this state is unstable. So if you see, it's stable. Okay? So that's a stable steady state. So it means that if I do a perturbation, I should not just go bananas. You should just do some sort of oscillation around maybe, but don't go and then kick it out. Okay? So that's a good lesson. You see, it's stable. So you're never going to see anything unstable because no pencils are upside down in the streets. All right? So this is the thermostat that we're talking about. Now, let me just do a different experiment. So I told you that this is a stable steady state, the one in the middle, with a specific distance. The question is now, what about if I perturb this one? For instance, what happens if I just do a perturbation so that there are no colors? I'll just use this. I perturb a little bit in this direction and a little bit in this direction. What's going to happen? So this is this experiment. And you see what happens in this experiment. The vortices are rotating. Okay. So this rotating is that amount, if you have done your differential equations class, that is equal to a center. It's a neutrally stable equilibrium. Okay, what is a neutrally stable equilibrium? You can have true equilibrium. This is a pendulum with friction, perturbation, close to a stable equilibrium. Now I'm going to do a unrealistic, that's what we do all the time in physics, the lossless Hamiltonian case. Okay, and I'm going to do an infinitesimal perturbation. This is an infinitesimal perturbation, so you can see, otherwise you won't see. Right? But imagine that this is an infinitesimal perturbation. What happens to this solution? It doesn't go further away, it doesn't get attracted, it just rotates away. And rotates is because if you go to phase space, position and velocity, you get circular ellipses. That's what is called a center. Okay? It's what's called neutrally stable. You perturb, you don't go back. But the most important thing is that you don't go to hell. You stay in a neighborhood, just rotating. So this is telling me that this is logical because this system is Hamiltonian, and we know that the steady state was stable because if I see it stable, therefore perturbations away from it should give me just some sort of rotations. And maybe if I linearize my effective equations of motion of the particles, I will be able to get eigenfrequencies that are going to actually dictate what is the rate of movement here that is going to be simply the imaginary part of the eigenvalue of my eigenfrequencies. If you know what I mean when you do something like this for these. So I might be not talking to all of the students, but at least a few. All right? Okay. So that's what happens if you do a symmetric perturbation out of the equilibrium of the stable equilibrium. Then there is this guy. In this one, I want you to pay attention on the angle between the vortices, okay? Minus 45, let's say. And let me just run it here. Oops, wrong direction. Let me run it. Kind of similar. But you see now the angle? The angle is no longer minus 45. So after some milliseconds of run, these start to rotate. And this corresponds not to a symmetric perturbation, but it corresponds to an asymmetric perturbation. And that asymmetric perturbation will give rise to two frequencies. A frequency of a rotation of a rigid body rotation that was very slow, plus the eigenfrequency of rotation around the steady state. So it's like two frequencies attached to each other. This one and this one. Okay? So out of this motion, you can get what is called quasi-periodic behavior. You can get periodic behavior if this frequency and this frequency are commensurate. That means if the ratio is rational, after a certain amount of turns, like a pretzel will close it itself. But if you, when you build a pretzel, or the least two figures, if you do cos alpha and sine beta, t, if alpha and beta are not rational related, it's never going to close. It's going to give you what's called a quasi-periodic. Okay? But the beauty is that you have put periodicities both here. Rigid body and the linearized eigenfrequency of rotation around the fixed. All right? Good. Okay. So let's try to put this into a quantitative kind of reasoning and the model. Okay. So first I need to tell you a little bit of what a vortex is. I just showed you this ball and I was talking about centrifugal force or whatever. But this is the math behind this one. I have a partial differential equation called the Grove-Vitellescu equation or the non-uniform equation. I want a solution that looks like this. I'm going to be a solution that has a radial profile. It has this e to the minus I mu d. This is kind of the energy of the system. Mu is what is called the chemical potential. So this is just the natural vibration. Every quantum object has a natural vibration in time. Okay, plus this term here that is telling me that the phase in the vortex is going to change. So there's this phase and it's going to change annually. The beauty about this quantum mechanical scenario is that this change of phase that is related to the angular momentum has to be quantized. Why? Because physics is continuous. So if I have a phase here and I keep on turning, after one turn, I need to match the phase. The phase cannot have a discontinuity because physics is continuous. So what is the only way that I can match the phase? Is that if I go with zero phase, zero phase, zero phase, zero phase, zero phase, zero matches zero. Or what I can do is after I do one turn, I increase my phase by 2 pi. So here I have phase 0, phase pi over 2, phase pi, phase 3 pi over 2, phase 2 pi. Can I join phase 2 pi with phase 0? Right, because the phase is defined up to 2 pi. So I can have these objects that have a phase that is an integer number of windings that are integer numbers of 2 pi k, where k is an integer. Okay? And that gives me vortices of charge 1, when you do 2 pi, charge minus 1 is if you do a turn and you do minus 2 pi, where you can have plus 2 and minus 2. We're only going to concentrate on plus 1s, minus 1s, because the plus 2s and minus 2 were higher, they're actually unstable. And a plus 2 vortex doesn't like to live like this because it's not the minimum energy state. The plus 2 vortex is better to be like that. Okay, this is higher energy than it. So vortex of charge 2 then you should split into 2 vortex charge 1. And it's difficult to create things that are unstable. So we're going to talk only about vortex of charge 1. So once you put this into your partial differential equation, you get just a boundary value problem for your radial profile. And your radial profile is given by this partial differential equation. Okay. The problem of this partial differential equation that gives you the radial profile of a vortex that depends on the charge. Plus or minus 1 is blue, plus or minus 2 is red. Obviously, the more charge, the fatter they are because of the centrifugal force. The issue is that this equation, my friends, it's just basically applying the Laplace in polar coordinates, doesn't have a closed solution. Don't look for a solution of this. There is no solution. No hyperbolic tangent, no hypergeometric Riemann data, whatever, call the function Jacobi that you can embed. There is no solution for this. So this is where my other tripolar Carretero guy comes into the play that you need to do numerics because there is no solution for this. So I need to solve this real problem numerically, but that's okay. I can find the states and then look like this, okay? So the vortex for you, I introduced the vortex. This is its density profile. This is vortex density, extend phase profile. And a minus will have the same thing here, but basically just mirror image because it doesn't go from 0 to 5 because of 0 to 9. This is a vortex, so right? Okay. So out of these guys, you can put them in a trap, and I'm going to tell you about the mathematics behind this, but you can put calculation analysis, match up and all the stuff that mathematicians we do, and you can get some sort of frequency of precession range. The closer you are to the center, your radius is with respect to the Thomas Fermi radius, remember it's the size of the cloud. So if you are at a radius 0, you're at the center, and you have an infinitesimally small perturbation, you're going to rotate with this rate, where S is the charge of the vortex. So one is going to rotate in one direction, and a minus one is going to rotate in the other direction, very close to the center. But you see that the frequency is adjusted by how far you're away from the center, because as you go away from the center, the slope is different. So the slope is different, you're going to rotate different. Electrically charged, as we get close to the edge, it's going very quick because the edge has a very, very steep slope. They rotate at a certain, and as you go out, they start rotating faster, faster. Okay? And this is a dynamical run using the Ross-Pitayevsky equation, using some integration of the numerics. And this is what you see. So this is basically an emulation of the experiments that you saw earlier. That's my vortex rotating because of the gradient of the underlying density due to the trapping that I have. Okay. And once you measure this frequency that comes from the math, you measure the frequency of rotation from the experiment, you get that beautiful. Good. So far, we're able to describe precessions for the precession of the vortex that trap. Perfect. And there is a way to obtain it from all the constants that your system has. Okay. Or like constants or whatever. You can actually quantitatively predict. What happens if I now put two vortices? Okay. That I already gave you the story. So if I have a plus and a minus, this is a plus and a minus, opposite charge. So let me just show you the picture, and then I do the same charge. So this is the opposite charge. I already told you what's going to happen. They're going to just go parallel to each other. Okay. So these are two vortices with the same charge in a homogeneous condensate, just because of the existence of each other. Like you do the pattern in the lake, they go parallel to each other. If you put a plus and a plus, or a minus and a minus, if you put the same sign vortices, what do you get? So this is a plus, this is a plus. This creates a field in this direction. This creates a field in this direction. What happens if you have two planets with velocities that are tangential and equal? You're going to get circles. Okay, that's what happens when you have planets. Right? So that's exactly what happens if you have two vortices of the same charge. They just rotate around each other. As you will see this in this little animation. And they rotate. Okay, perfect. So you see that I have now described the two forces, and I don't know if you notice, every time that I say the word force, I've been doing this with my hands. Forces is Newton. Newton equals F equal ma. Second order quantities, second derivatives. That's a force, that's a true force. These are not forces, these are velocities. Okay, so these are first order forces. First order forces just a velocity. So that's why I say forces just for you to kind of get the picture. Those are not forces, they are just really velocities. And it's different. Because a first order equation and a second order equation is not the same. Okay, but I'm going to keep on saying just forces, but I'm going to do this with my hands so that you know that I'm doing just the direction that is velocities. So as I said, before I was losing track, I have the two essential ingredients. I have the forces between vortices, and I have the forces that the background drop is imprinting in each one of them. So now I can describe the experiments, because I just add the two forces together, and I will be able to get a nice, beautiful dynamical system, like if there were planets. Planets is F equal ma. It's not F equal ma, it's first order equations. So you're gonna see now first order equations, but a la planet-like or a la particle-like. Okay? Here it is. So these are the equations of motion that come out of a soup of vortices. I have n vortices, each one of these charged. This term here takes care of the rotation in the trap of each one of them. And this one, trust me, is the one that tells you how two vortices are gonna rotate around the disorder if they are of the same side, or they're gonna go in a line if they are of opposite side. These are my equations of motion. The position of each guy depends on the position of all the others. That's a nice differential equation. Actually, it's a set of differential equations. It's for n vortices, I'm gonna have two n equations, one for the x and one for the y. If it's a Newtonian system, for n particles, you have 4n in two dimensions, you have 4n equations. You have the x, the y, the velocity in x, and the velocity in y. Okay? So this is not Newton. Okay? This is what's called advection, just first order. Okay. This is my equation of motion. Now I give this to a mathematician, dynamical system person. What do you do in order to find a steady state? What is a steady state? Nobody moves. Nobody moves. The rate of change is zero. If the rate of change is zero, the right hand is zero. Just find me all the positions, all the vortices, so that the right hand is zero, and that find me all the collections of possible scenarios where nobody moves. So just find the right hand zero. Okay? So that's the exercise I'm going to be doing now. A mathematical exercise of finding the zeros of the right hand side, evaluating the Jacobian of the right hand side to give me the eigenvalues for the stability of the right hand side, to do stability. And that probably is going to give me, in some instances, a change of stability. Change of stability being a bifurcation. Okay? That's what we're going to do with the next 45. Okay. All right. Interesting. These equations have two constant quantities. One is related with the angular momentum, and the other one is related to the Hamiltonian. And you can see that those are constants of motion. It's interesting that if I have two vortices, I have four equations of motion. But if I have two constant quantities. So what is the crazy stuff that I can get with two vortices? Two frequencies. Two frequencies is, if they're commensurable, it's periodic. If they're non-commensurable, quasi-periodic. That's the worst scenario that you can get, the craziest. So the craziest, the net crazy thing is take three vortices. Three vortices are 6 equations of motion. Two constant quantities, I have a 4-dimensional system. If you know your theory of dynamical systems, with 3 or more dimensions, you can actually get chaos and crazy shit like that. But in order to get that crazy stuff, you need 3 vortices or more. 2 vortices is boring. Okay? It's boring, but still gives you a very nice bifurcation process and you change 6, and we're going to see in just a bit. But now we're going to concentrate into states that have just 2 vortices. So let's talk about the plus and the minus. Remember the plus and the minus? This stationary perfect location, where if you perturb, you have this rotation. Okay. Let me analyze this at the level of the ODE model that, remember, physics, multi-body Hamiltonian theory, mean field theory, the partial differential equation, nonlinear general graph mechanistic equation, perturbation, variational, match asymptotic, I don't know what bullshit the mathematicians do, ODE. The ODE, I do dynamical systems, I get a steady state. Now I want to connect all the way to back here, okay, and see if I can, right? So I want to see something about actual experiments after all this process of level simplifications. But this is what I want to describe. So it turns out that indeed, there is a specific steady state that it turns out to be stable from the ODE perspective. And that one, when I perturb around it by using just the Jacobian and evaluated the eigenvalues, I'm going to have the imaginary eigen frequency that this guy is just going to put. And I can measure that, or I can compute that from the ODEs, and it will give me a number, and then I go to the experiment and you say, what? They match. So I'm pretty able to predict this type of motion. Okay, that was for the symmetric perturbation out of the origin. Beautiful. Good. All right. Now, let me talk about the asymmetric. I'm in the stable. I don't do an symmetric one. I do an asymmetric perturbation. The asymmetric perturbation can actually be cast in such a way that Both of them rotate at the same rate on a co-rotating frame, one at a distance R1 and the other one at a distance R2, diametrically opposed. So R1 and R2 are positive, but with the sign minus, I'm on the other side. I'm gonna be on both sides, both of them are gonna rotate a rigid body at the same rate, but it's gonna be an asymmetric state. I plug this into my differential equation and I try to look for these co-rotating asymmetric states. And they do exist, and I can find them. Steady states. In a co-rotating frame, I have to be co-rotated. But when I'm co-rotating, I see them. If you co-rotate at the same rate, it looks like stationary states. Okay? Perfect. So I have now these stationary steady state. Skipping a little bit of the math because I've been focusing too much on the physics and having too much of it. So skipping a little bit of the math here, but it's not difficult stuff. Okay? So this is second year stuff. No words. All right. So what you see is that the experimentalists, when they put these two vortices and measure how they were moving, they look at this very intricate patterns, and they didn't know what they were seeing. So when I just present this to you, it's not just like some crazy figures. Oh, maybe this one, some sort of rotation without rotation. But this one, I don't know. This one, I don't know. Don't worry. Professor Carretero to the rescue. You give me the initial conditions, and I will tell you what is the co-rotating frame for that specific asymmetry. And I tell the experimenter, of this frequency. And okay, you do it. And this is what you see. Well, the crazy stuff that the experimenter was seeing is nothing but a perturbation of an asymmetric stable state that you get a center. And you can just get this in a co-rotating frame. And now you see that the orbits are pretty clear what they are. Very small asymmetries, or no asymmetries, very small co-rotating frame. Very large asymmetries, very fast co-rotating frame. But it's logical. Okay, good. Okay, that was the whole story about a +1 and a -1. Interesting, but not groundbreaking. The next one is even more beautiful. This is a plus and a plus. Okay? Two vortex, two charges, vortex of charge 1. I'm going to skip all the math. Okay? So if you have a plus and a plus, the plus and a plus rotate like this. A single one in the track rotates like this. All the forces add up together. So there will never be a truly stationary state. Because this has net angular momentum that is not zero. Therefore, the only thing that will exist are co-rotating states. So I mount myself in a co-rotating frame. So I just use polar coordinates and the relative distances of the relative angle between the two guys. So I just cast all these as I had before, but in polar coordinates and in relative radius and relative distances and relative angles. You do this, you do all that stuff. And once you have your system and you perturb it, you get these varying frequencies of perturbation. So I have steady states in my rotating frame, and I'm going to be perturbing. And these are the frequencies coming out of there, where R star is the radius at which this pair is lying. Okay, so I can change the rate very nearby or very close to the edge. Very close to the center, okay, this term is very large. Okay, and this term is negligible. I'm rescaling all the R's with respect to RTF. So R equals to 1, you're at the edge, and you're turning very quickly. Okay, so R goes to 0, I have omega squared equals to something positive. Therefore, omega is a real number. Omega real number is that you have positive frequency, therefore you have rotation. For large radii, this term is small, and this close to the edge is going to be very, very large. You have an imaginary frequency. You have an imaginary, yeah, you have a negative square of the frequency. You have an imaginary frequency. Imaginary frequency tells you, instability. So this predicts that there is going to be, when these two terms are equal to each other, there is going to be a threshold distance when this guy must be stable. Also, it's interesting. Two guys close to each other, have to be married, they go around that stable. I can place them after that R star, and this guy is a pencil upside down. They don't want to be there. And they should be stabilized. Right? So you get what is called this bifurcation rather. Small vortex dipoles, they are stable. Large vortex dipoles are unstable because they bifurcate in what is called a pitchfork bifurcation, because this is a theory of dynamics. Something will go from stable to unstable, but there has to be something else that is at play. So this other branch is that asymmetric states come into play, and they bifurcate from the symmetric states, and they take out the stability of the small dipole, so that the large dipole is stable, and there is this branch of asymmetric states that are stable. So this is what my math is telling me. So what happens if I now do the experiment? And let me tell you a little bit of how they do the experiment. The experiment, they just sphere, and they create vortices. They cannot place them where they would want. So I got a bazillion movies of vortices at random locations. What should I see? I gave you this bifurcation diagram. You should tell me what should I see. You should not see TensorFlow right now. At least I haven't yet. 5 years. What should you not see out of all the movies that the experimentalists said? Tell me. Can I see this? Can I see this? Can I see this? Out of all the movies that they're going to send me, there will be anything that is symmetric should be smaller than a certain radius. If it's larger than a certain radius, it has to be asymmetric. And that's exactly what I was going to explain. Out of all the experiments, hundreds of experiments, we were categorizing everything. And we will show that for every single thing that was rotating as a rigid body, and it was not perfect, it cannot be perfect. There was a perturbation. But that perturbation, because unstable, just does this. So in the color rotating break, it stays. Okay? And anything that was larger than this critical radius, it actually got distorted and got destroyed. Out of all of them, you can do this trick with 3. You can do this with 4. And actually, you can do the experiments with 3 and 4. Every time we saw a more or less equilateral triangle with a perturbation, it just danced and it went in a color rotating frame. Any triangles that were larger than their critical radius, they got destroyed because they never see it stuff like that. And then you do the 4. A 4, little perturbation, because I cannot start with the exact thing, it's going to dance, but I will never be able to see a quad that is larger than a certain critical radius. And it worked really fine. And with this, I'm going to end because I'm not going to be able to do the 3D everywhere. And I thank you for your attention. And I will be answer any questions until tomorrow.
Thank you very much, Ricardo, for the nice presentation. Let's have a few questions. Let's start with the graduate student, the honor student first. Do you have any questions, please? Okay, please.
Maybe this is just, like, I don't know enough about these, but we talk about imaginary eigenstates, and that is a sign of instability. Can you kind of elaborate why?
Sure. When you linearize your system and you get an eigenfrequency, so you get a solution of your linear differential equation that is an exponential. And then the system has I omega t. What happens if omega is real? Omega is real, you have a rotation. Omega will be omega r plus I omega I. What happens if you have an omega I that is different from 0? You have I times I drops. You have an exponential. And if you have a negative, here you're going to get a negative exponential. Because it's Hamiltonian, you will always get the e to the plus I omega t and the minus omega t. So for a negative eigenfrequency, you replace back into your solution, you're going to get exponential growth rate. What is exponential growth rate? It's exponential growth rate. At least at the beginning, it's exponential. It's an instability, it's an exponential growth. And that, you started by saying, I don't know too much about Boston condensate. You have eliminated all the stuff that you said. This is for any physical system that is Hamiltonian. Okay, so erase the first half part of your question.
Okay, let's create a new question. Okay.
I might have just missed this, but whenever you were talking about the critical radius, was there a relation between like 2 vortices with critical radius and then 3 and 4? Like how does the number of vortices affect the critical radius?
Right, the larger the number of vertices, the smaller the critical radius. But I did not talk about it because I actually didn't write. But yes, that's what.
Can I just in the experimental setup, what kind of like materials are you using to like make these vortices? Like how are you?
Any boson that you want, in principle, you can condensate. Because bosons have the quality instead of fermions that can operate the same quantum. So boson and condensation is in principle possible for any boson that exists in the universe. Just the critical temperature for my derivative wavelength to be of the same order of magnitude as my interparticle distance might change. Okay, these guys are done routinely in rubidium, in lithium, in sodium atoms. But in principle, any boson can.
How can you stir the vortex statement?
How do you stir the condensate? You grab a spoon from the cup and you do those things. Yeah, you do that. It's just the spoon is disconnected. How do you steer it? Physically, you steer it to that. That's it. That's it. Actually, there are several ways to do it. This behaves like a superfluid also with all the properties. So if I have a container that is isotropic in a superfluid, you can do that. If you have superliquid helium here in the whatever, you try to turn the container, you see that the superfluid is going to do nothing because you don't have any friction. So you cannot have a symmetric and rotate the symmetric container and impart angular momentum into superfluid. So what they do is they do a trap that is oblong. When you do the one of the oblong, then you can impart angular momentum. So these are the main 2 ways: laser or trap that is rotated, but not a isotropic angular isotropic trap. It has to be an anisotropic angular trap.
Okay, let's have one last question maybe with the meeting student. Any last answer?
How long do these states live?
So the condensates have a spatial size of microns and their temporal size of the 100 of milliseconds. Some experiments go all the way to a second. After that, you get 3-body recombination effects. They heat up, you go up the temperature, and they're killed. But basically, you get on the order of seconds in time and on the order of microns in space. That's the size.
So it's more of a like, restriction on the experiment, not so much the theory of it. Like in
Well,
principle,
in theory, if you have a perfect condensate at temperature T equals to 0, that will never reach because you need an infinite amount of energy to go temperature 0. But then in principle, this thing will be loaded. But you don't get there. Nanokelvin is the best. And at nanokelvin, you have a small fraction of thermal atoms that are not condensate. They interact with the other atoms and they keep them up. It's straight edge. So very good experiment, everyone over tens of seconds. But that's okay because you can still see things moving in that range.
Okay, let's thank our speaker.